previously, when talking about Eisenstein series and sort of all the technical formulas that are associated with them, we wrote down the following. So this is the notation of this previous lecture, and these are completed Eisenstein series attached to characters. So the reference for this is Matthew Young 2019 paper, Explicit Calculations with Eisenstein Series. And we wrote down the Fourier expansions like this. Here tau is the Gauss sum. Lambda here is the completed Dirichlet L function. Here sigma is the sum of divisors function, twisted by Dirichlet characters. And then we have our Whittaker function. This is the K-Bessel function. And here I'm going to write E of nx just as shorthand for e to the 2 pi I nx. So this was one of the two completed Eisenstein series attached to characters, and this was the other one that we're going to need. Here, one is the character mod 1. So this one's Fourier expansion was as follows. And the point of these is that you can easily express the Eisenstein series attached to cusps in terms of these. And these tend to be easier to work with in pretty much every way. I should say this is all for n prime, and chi is even and primitive. So we get this nice looking Fourier expansion. And then we also said in that lecture that there was a functional equation. The functional equation for these Eisenstein series was that E of chi1, chi2 completed at Zs was equal to E, and then here you had to swap the characters and conjugate them, and then you have at Z1 minus S. So this was the functional equation. And this is very easy to prove, so let's just let's prove this by just looking at these Fourier expansions. So let's start with the constant term. Here we want to say, so let's look at this one, and let's swap the two characters, conjugate them, and then replace S with 1 minus S. So here we get this let me write this out a little bit more clearly. What our functional equation is saying is that if we take the first thing that we have and we apply the functional equation, we have to swap the order of the two characters and conjugate them. So of course one conjugate is just 1, psi bar is psi, and then here we have z 1 minus s. So basically it's saying that this top thing, this top Fourier expansion, should be the bottom Fourier expansion, but with s replaced with 1 minus s. Or maybe it's going to be a little bit easier to do it this way. Maybe we'll put the 1 minus s here and the s here. Okay, so let's look at this and see if that's true. So let's start by looking at the constant term. So when I say the constant term, what I mean is the term that is constant in x. So this part is the constant term. So the constant term here is going to be n, and then I'm going to write 1 minus s instead of s. So it's n of 1 minus s over tau of psi bar times the completed Dirichlet-L function of 2 times 1 minus s, so that's 2 minus 2s psi bar, and here you have a y to the 1 minus s. And that's equal to the constant term here, right? That's exactly this term. So the constant term satisfies this functional equation just sort of automatically. What about the non-constant terms? Well, this part, the Whittaker function, the square root y, is going to stay the same. The e to the nx is going to stay the same. So the first part to look at is this k-Bessel function. So the k-Bessel function, k of 1 minus s minus 1/2 at 2 pi n y. So this is equal to the k-Bessel function at 1/2 minus s of 2 pi n y. And it turns out that you can always put a minus sign in this argument and get the same thing in your k-Bessel function. So let's see that now. So let's look at k-Bessel function at, say, u, y. And remember, by definition, this was 1/2 times the integral from 0 to infinity of e to the minus y times t plus t inverse over 2 times t to the u dt over t. This was just our definition of the k-Bessel function. And now let's make the change of variables. U goes to minus u. So u goes to minus u. That's the same as just t goes to 1 over t. And that's the same as t maps to 1 over t. Now dt over t is the Haar measure. So it's going to be invariant under this transformation. And we can just check this directly, right? That, if we have ddt of 1 over t, that's minus 1 over t squared. So this is going to be, or this is going to imply that dt over t is equal to d 1 over t over 1 over t, both a minus sign here, coming from here, but we also have to swap the bounds of integration. So invariant essentially after swapping the bounds. I don't know how you want to think about that. But anyway, this is invariant under this transformation. Because you also have to do 0 to infinity goes to infinity to 0. Okay? So here we can just stick a minus sign here. And then in this exponential, if we replace t with 1 over t, then these two terms are swapping. So this thing also stays the same. So this ends up being equal to k minus u y. Okay, so what that means is that this k-Bessel function that appears in the Whittaker function, it is invariant under s goes to 1 minus s. Right, because the end result is that we're sticking a minus sign in front of the s minus 1/2. All right, and then what about these Fourier coefficients? So the 2 is going to stay the same. So let's look at n to the 1/2 minus 1 minus s sigma of 2 times 1 minus s minus 1 and psi. Right, so that's exactly this Fourier coefficient here, except we've taken the s and we've replaced it with a 1 minus s, which is what we're trying to do, and we're going to try and check that we get exactly this thing down here, and we do immediately, right? So this is n to the s minus 1/2 sigma of sigma of 1 minus 2s and psi, and that's exactly what the Fourier coefficient is here. So essentially, just by replacing s with 1 minus s in this top Fourier expansion, we get the bottom Fourier expansion. So that verifies the functional equation in this specific case.